In Module 3 of Chapter 21, we're going to investigate the Black-Scholes differential equation and real returns. In the Black-Scholes differential equation, there is no mention of the return alpha that the stock is expected to earn in the real world. We price only with regard to the risk-free rate, and we saw from our binomial pricing models that this was related to the idea that we had a risk-neutral probability of stock movements and the risk-free rate. And we saw in that context, using some utility theory, that in fact we could price in the binomial lattice either using the risk-free rate and risk-neutral probabilities, or we could price using a risk-averse utility approach, which reflects risk aversion, but we need to use the appropriate rate of return on the option, and we get the same price. And the goal of this module will be to show that, in fact, we can construct a Black-Scholes pricing approach using real returns. However, when we make the appropriate adjustment for what those real returns must be in relationship to the risk of the option and the stock, we'll find that it ultimately reduces back to Black-Scholes. So there's no way of forcing the differential equation to reflect an alpha except notationally, and that once we accommodate what alpha needs to be, it will be in the algebra. It will find that it disappears. So what we'll begin to do is looking at how to generalize this partial differential equation, starting with a stock that explicitly reflects the return of alpha that the stock earns. And we do that, of course, applying Ito's lemma, where we assume that S satisfies geometric boundary motion with the real-world parameters. So here we're making a model where ds is equal to alpha minus delta s dt, and then we have a sigma s dz. So we're using the real-world parameters, and Ito's lemma then tells us that, okay, any derivative security must satisfy in the real world of this process. So from this process, we can look at the expected return, the instantaneous return on this option. And what is that? It's the expected value of dV divided by v dt. So alpha we can think of, because notice we have a dt in the denominator here. That tells us that alpha is an annual return. It's an annualized return, because if I wanted to know the expected return of dV over v, I would multiply alpha by dt. Okay, so by dividing by dt, when I look at the expected value, the expected change in the option divided by the initial option price, what I would get otherwise would be alpha option dt. And so by dividing by dt here, this alpha is an annual number. So it has the same time units as alpha, delta, sigma. It's an annual number. Now where does that come from? Well, you'll notice that this numerator is the drift. We have the Ito process. The drift term tells us the instantaneous expected change, because why? This has an expected value of 0. Right? That's the whole point of dz. dz is normally distributed with a mean of 0, and it has a variance of dt. So if I do an expected value, it goes away. In addition to the expected return on this option in the real world, we have an expression for that, we can also look at the unexpected return, the risky part of the return. And how do we do that? Well, we simply take dV over V, that's the actual return, subtract the expected return, and we get this expression. Namely, the price of S, Vs, the delta, divided by the price of the option V times sigma dz. Now notice that the this sigma option is this expression. So it's saying that the unexpected return has a volatility that's proportional to the volatility of the stock. And the proportionality factor is a formula that might look familiar to you. We've seen it before. And then we have the dz term, which of course reflects the time period square root of dt and the normal variable that's embedded in that Brownian motion. And so we could think of this as the unexpected return is the sigma option, and then we have a normal variable times square root of dt. Right, so if you wanted to think in terms of the units, the time units, that's the units of that sigma option.